friends. Good morning, good afternoon, good evening. We are live with Baji. Baji has been helping me clean, so today we woke up kind of late. We were very tired after last night's live, and even though I woke up in the morning, then I stayed in bed a little bit, and then we just finished cleaning and eating some food and getting situations organized and doing bathroom cleaning for the kitty cats. And now here we are. Suji Mama is upstairs, but Baji Baba has braved the downstairs after all the vacuum cleaning noises. Look at him. Look at how brave he is. A brave Baba. He's a brave Baba. And we are live. Welcome to the live. And I'm going to maybe share the live and make some coffee and hang out. Yay! Baji Baba! Baji, look at Baji's face. Baji's face is extremely stoic right now. Baji, are you feeling stoic? Baji, are you a stoic? Are you Plato? Are you Copernicus? Ooh, and also, once we are settled with the hangout and once we are caught up, once we are settled down and once we are caught up, I'm going to also talk about planets. So there will be that as well. There will be some planetary stuff as well. Baji, are you an owl? Baji looks like an owl. And Fuji Baba is here too. He has been helping me tremendously with picking things up. Let's see. Baji, look at that. Big stretch. Big stretch. Thank you for coming to the live. Welcome. Hi, Ram Candy. Hi, Good Sir Fry. Now here's a live stream I can agree with what they're saying. Aww. Ram Candy, how are you doing? Thank you so much for coming to the live. Thank you so much. Welcome to the live, and thank you for liking the live. Yay. Thank you for liking. I'm gonna be under the blanket. It's a little cold. I just finished cleaning and now I'm a little cold and I need to make some coffee and I need to eat something. But then I am more than excited to hang out with everybody and catch up with everybody. And we're gonna talk about a few interesting topics as well once we settle down with some planets and their moons. Ram Candy, hello. Good Sir Fry, hello. Cats, yes indeed. Bradley says hello. Hi Bradley. Hi Good Sir. Hi Ram Candy. Hi, look at Baji. He is extremely cozy right now. Just a cozy baby. How is everyone doing? How is everyone doing? Thank you. Thank you for liking. I see the hearts. Thank you so much. I'll give myself some hearts too. But if you could like the live, that would be tremendously amazing. Yay. Hi, Baji. Baji Baba. Look at this. Look at these nice little designs on Baji. Look at this nice design. Hi, Baji. So, last night we had a live and we talked about the universe and cosmology and how the universe got started and the Big Bang and all of that stuff. And Suji Mama appeared on the live and she got some hugs and kisses and she was like, well, I need some more attentions and loves right now. Over there is Fuji. Fuji took a nap last night during the live. Right now, see how he is awake and he is very much supporting this discussion and he's overseeing the conversation and he's more like a manager in the house. He is the security officer and site lead of this home. So he makes sure he's like a guard cat. Some of our friends have mentioned that he's a guard cat who will oversee and look after everything. And Baji here is more like the baby. He likes to kind of sit and be pretty. He believes in sitting pretty amidst ancient ruins. Not really, but he has that Roman vibe, Egyptian vibe. He's like, I want to be pretty amidst the ruins. I don't want to be ruined myself. So he believes in getting massive amounts of love and affection and wonderful experiences in life. So that is Baji. Yes, thank you for the emojis, Bradley, and the next person whose name I can't quite read, but Kat. Thank you, yes. Oh my gosh, look at all the love you're getting, Baji. Baji Baba, closing his eyes. He likes to close his eyes and contemplate his next meal and contemplate what is really important in life. It is to breathe nice and fresh air, to get hugs and kisses, to eat and enjoy your foodie, to drink enough water, and to go and demand affection and attention from all of his siblings and mama. In this home, he is extremely loved because he makes sure of it. He's a very communicative person. Indeed, he cries a lot when love is not freely given. He is very demanding. He knows how to communicate and let you know that it is in fact wanted. Oh my goodness. Before I met Baji, I wasn't sure whether kitty cats were capable of this level of communication. But from day one, when I met him at this particular cat cafe rescue shelter thing, he was extremely young at that time, but he made sure that he communicates his needs profusely, and he himself walked into the little carrier bag that I brought. And actually, I was trying to adopt his sister, who is now currently upstairs. Thanks to the universe for these babies. Baji, he is now curled up. He's now curled up. And look at Fuji. He is extremely alert. He's watching that Baji can have a nice nap. He will oversee it. So Fuji oversees all the naps and all the things that happen here in the kitchen, living room, office, everywhere. Hi, Gerald. How are you? But yes, the adoption story for Baji is that he adopted himself and adopted us and made sure that he came home with his sister in the same bag. I brought one bag thinking I'm going to come home with the one kitty cat, but he also was in that bag. I like cats. Oh, good. Thank you for joining, everybody. Thank you for being here. So very nice of you to come into the live. Welcome, welcome. We will have a slow and take it slow kind of chat and hang out. Look at Baji. He has set the mood already. If you want to take a nap with our kitty cat chat and voiceover, you're most welcome to start to take it slow and what day is it? It's Thursday. So I'm hoping that you are ready to kind of take the week to a close and start unwinding and feeling more peaceful and relaxed and just kind of starting to be and let things be, just like Baji. See how he lets things be, like the vacuum cleaner. The vacuum cleaner was making a lot of noise, and I had to do some cleaning. See how it's looking? I think it's looking better now. There's a lot of cleaning happened here just now, right before the live. Cool MD, hi. Cool MD says hi. Hey, how are you? So he just kind of lets things be and just relax, chill, peace, sleepy, nappy time, nap, sleepy dippy. So when the vacuum cleaning is happening downstairs, he promptly goes upstairs. He finds a window of opportunity where he flings himself into the hallway over there from this couch atop, and then he starts to run at full speed upstairs to join his sister, who is already upstairs because her intuition is extremely sharp, and she already knows when the vacuum cleaner is going to be coming out, even before it is out, because that is called vigilance and being alert to at a whole another level that his sister is capable of. So then he goes, so Baji's usually the last one to find out that vacuuming is going to be happening. Everybody else knows already. But then ultimately he goes and joins his sister, and he lets it happen and he lets things be. And then now he missed Mama, and now he's back down because social is important to him. He doesn't want to be by himself upstairs, or relatively by himself. There is one more kitty cat upstairs who is his sister, but he wanted to come back down and join everybody. So thank you everyone for joining the live. Yay. Baji really believes in being social. Look at his facey. Baji, are your eyes closing? See, he woke up because Fuji is shaking their dispenser, their food dispenser. And see, again, he lets things be. He's just like, okay, if Fuji does something and food does come out, then maybe I'll get up. But if not, then, well, I'm quite cozy. So the food is up on the counter because I was cleaning. So Baji, yes. Hi gamer coder. Hi gamer coder. Hi gamer coder. Actually, let me share the live one more time and give Fuji some reassurance that he is imagining himself to be hungry because they've eaten quite recently. And let me type something in the chat. Hi. Let's chat. Fuji Baba. Ooh, and I need to make a, what do you call? Make a coffee as well. So I appreciate your patience. We will keep chatting. So, you know what? I think what we will do today is we will cover the moons of Jupiter and Saturn in just a little bit here, and I will just be doing the kitty cat hangout and my voiceover for the planets and their moons. Let me type the sharing of this live. Um, let's see. We are live with kitties who are sleepy deepy. Yay! So during the night lives, I usually I usually what do you call will be on camera and do all the things where I talk directly to the people about physics, cosmology, astronomy, astrophysics. But then sometimes I mix it up with a live like this where we're just kind of hanging out with the kitty cats, and it's chill and it's peaceful, soothing, relaxation content. And then my voiceover tells you something about science and planets and whatnot. So that's kind of what this live is going to be. Gamer Coder says, Catloaf. Yay! Yes. Again, everybody, thank you so much for being here. Yay. Oh, Fuji. Oh, Baji. So that's what we are going to be doing. Thank you, thank you, thank you, everybody. Thank you for being in the live. One thing to kind of note is the book that we will be using today is this book, Foundations of Astrophysics by Barbara Ryden and Bradley M. Peterson. So, indeed, we will be covering from this. And what we have been doing recently is we were talking about the planets in our own solar system. And we talked about the rocky, metallic, terrestrial planets already. Those are, of course, our own planet Earth, Mars, Venus, and Mercury. So we covered those planets already. Today we will talk about the planets Jupiter and Saturn. And actually, in a past live, we kind of started this topic already. So today we will go straight to the moons of Jupiter and Saturn, which are generally a really hot topic. People are interested in these moons for various reasons, and they're also a very current, active research topic. So that is what's going on at this time. We will get started shortly. Please enjoy the kitty cats and the peaceful time while we're at it and whatnot. So let me look at the Mac one more time and let's see. The chat is good. Yes, okay. Go into start planets soon. We will cover Jupiter and Saturn moons today in a bit. I need to make my coffee first though. Hang tight and feel free to put anything in the chat and I will read your messages as well. Thank you. Okay. Very, very nice. Oh, and did you see that it's daytime now? I like the daytime lives because they are good about and whatnot. So, in fact, what I could do is the following. Okay. All right. Sorry, I was a little distracted by my Mac here. Okay, so we will actually get started, and in a few minutes, I might get up and make some coffee. So Jupiter and Saturn. So by the way, I have a live earlier in the channel. Basically, if you look at my live tab, if you're looking at this as a video upload later on, that's completely fine too. And if you're in the live right now, then welcome, welcome. Thank you so much for being here. And under the live tab, just a few days ago, I believe I had a live stream episode called Jovian planets. Basically, what that means is the Jupiter-like planets. So pretty much, the planets that are farther away from the sun, such as, of course, Jupiter, Saturn, Uranus, and Neptune, are very different from the rocky, metallic planets, including Earth. So these other planets are sort of grouped together as the Jovian planets. And even within the Jovian planets, Jupiter and Saturn are much more kind of a group together, and Uranus and Neptune are sort of in another bit of a subcategory of their own. So oftentimes you might hear us talk about Jupiter and Saturn together and Uranus and Neptune also together later on. Now, of course, Jupiter and Saturn are also very much bigger. So Jupiter has the mass of 318 times the mass of the Earth. So extremely big indeed in mass. Peter, hello, Peter. Good morning. Peter, good morning. So once again, the Jovian Jupiter-like planets in order of increasing distance from the sun are Jupiter, Saturn, Uranus, and Neptune. Jupiter is 5.2 astronomical units away from the sun. Astronomical units is the distance between the sun and the earth. So it's a unit of distance that is often used in astronomy. So we are 1 astronomical units away from the sun on earth here. And Jupiter is more than 5 times away from the sun. So 5 times the distance away from the sun. So once again, Jupiter is at 5.2 astronomical units from the Sun. Saturn is 9.6 astronomical units. Uranus is 19.2 astronomical units away from the Sun. And Neptune is at a distance of 30 astronomical units. So you can see how Uranus and Neptune are even really much farther away. And you will see how these planets are also kind of different in their mass. So absolutely the most massive, gigantic planet is, of course, Jupiter. Some people, I think in my live a few days ago, people were calling it the failed sun. It's almost, this massive, it belongs in its own league kind of planet with a mass of 318 times the mass of Earth. Saturn is also big, but not as big. But we still club it together with Jupiter because that is the next planet, which is so massive. And that too, it has a mass of 95 times the mass of Earth. So 318 and 95 are still very different. Jupiter is still much, much bigger in mass. But Saturn has a pretty big mass too. Then we have Neptune at around 17 times the mass of Earth and Uranus at around 14.5 times the mass of the Earth. So you can see how these are kind of smaller and very different. So there are many properties that the Jovian planets have in common. They're all massive bodies that formed far from the young sun where the temperatures were low enough to allow condensation of volatile ices as well as refractory rocks and metals. Thank you, Ben. Checking in. Can't stay for the live. However, will return and watch all later. Gave a thumbs up. No. Thank you so much. Yes, please. You can return and watch it later. Thank you. Sorry about the, different time. And we might be able to go live again tonight as well. But thank you so much for being here. Yay. So these planets, the Jovian planets are, of course, they're all massive bodies that formed kind of far from the young sun. And these temperatures, so far from the young sun, of course, means that it is less hot away from the young sun, and even the current sun. And so the temperatures are low enough for these planets to allow condensation of very volatile ices as well as refractory rocks and metals. So you will see how the materials within these planets are quite different, and there's a lot of ices. And we will even see what these types of ices are. It's not all not all ice is water type of ice, okay? So the Jovian planets all have very strong magnetic fields. So we're kind of summarizing them all together at this point, and then you will see we will focus on Jupiter and Saturn a little bit more later on. But they all pretty much have very strong magnetic fields, and they're all very rapid rotators. So they rapidly rotate on their axis. We actually saw how Venus is a very slow rotator, and even Mercury had a very commensurate orbital period versus its sidereal period, as in how it rotates is kind of really slow and almost kind of similar to its period around the sun. So very interesting indeed that these smaller planets have that type of feature. But anyways, the bigger planets, the Jovian planets, Jupiter, Saturn, Uranus, and Neptune, are all rapid rotators, and you will see how this affects their magnetic field, making them have strong magnetic fields. How are you doing today? You have the day off. Enjoy your day. Thank you. Yes, thank you so much for being here. So the Jovian planets all have strong magnetic fields since they are rapid rotators and contain large amounts of electrically conducting fluids in their interiors. They all have multiple satellites, the largest of which formed simultaneously with their parent planet, and they all have ring systems. So they have multiple satellites. So another big thing about these Jovian planets are, of course, they have a lot of moons. You know, the smaller planets, the rocky planets, some of them don't even have moons, like Mercury and Venus. And we on Earth have just the one, a very amazing moon. Of course, it's a giant moon, one of the biggest moons of the solar system, but we only have one. So another big characteristic, kind of different about the Jovian planets, is that they have a lot of moons, a ton of moons. And the biggest of these moons basically formed simultaneously with their parent planet, is what we think. And another thing is that all these planets have ring systems, of which Saturn's is, of course, by far the most spectacular. So Saturn's rings are extremely famous, but they all actually have ring systems, the Jovian planets, okay? So anyways, those are some of the sort of overview of the Jovian planets, Jupiter, Saturn, Uranus, and Neptune. We actually, this was a little bit of a recap. We covered some more details about Jupiter and Saturn, especially some math that we covered a couple of lives ago, which covered about their central pressures. So because Jupiter and Saturn too, and especially Jupiter, have such high masses, they're extremely massive bodies, as in the mass contained within them very, very large, okay? So this actually makes the sort of layers within these planets kind of very interesting, and the central pressure within these planets is very, very high. So real quick, I'll recap for you that basically the central pressure within Jupiter and Saturn are in the millions of atmospheres. So I'll read this part right here. For Jupiter, the estimated central pressure is around 1 times 10 to the 12 Newton per meter squared, or around 10 to the 7 atmospheres, which 1 atmosphere is the pressure on Earth at sea level. So compare that to 10 to the 7 atmospheres, so over 1 million atmospheres. And then compared with Jupiter, Saturn is lower in density, and approximately the central pressure in Saturn is 2 times 10 to the 6 atmospheres. So still over 1 million atmospheres. So atmosphere, ATM, is in short, atmosphere is another unit. So you can express these pressures either in a standard SI scientific unit, which is newtons per meter squared, where Newton is a unit of force in the standard system. Meter squared is, of course, an area, meter being a length. So either you can say a pressure in terms of Newton per meter squared, or you can say it in another type of unit, which is atmospheres, which people sometimes find helpful, especially because on Earth at sea level, the pressure is 1 atmosphere. So pretty much if you compare that to Jupiter and Saturn, pressure of millions of atmospheres is basically what you're getting. And one very cool and important thing is that at these types of atmospheres worth of pressure, at these very high central pressures, hydrogen becomes a metal. So, something cool about Jupiter and Saturn is that they actually contain metallic hydrogen in them. There is a substantial layer. So, just like, we have rock at the center on Earth here, Jupiter, Saturn, Uranus, and Neptune also all have rock in the very center. But then Jupiter has rock and then ice and then a lot of metallic hydrogen, and then molecular hydrogen are the layers of Jupiter. And for Jupiter, this metallic hydrogen layer is extremely big. It's the biggest one as compared to everybody else, and Saturn has this too. So Saturn also has, albeit a smaller, but pretty much also rock, ice, metallic hydrogen, molecular hydrogen are the layers of Saturn. And this metallic hydrogen layer is missing in Uranus and Neptune, who only have rock, ice, and molecular hydrogen. This picture is right here. You can see that. That might be a better way than to hear it from me. But right here you can see Jupiter, bit of rock, bit of ice, metallic hydrogen, molecular hydrogen. Saturn, bit of rock, bit of ice, metallic hydrogen, and then molecular hydrogen. And then for Uranus, you have rock, ice, and then molecular hydrogen. Same thing for Neptune. So those are some interesting characteristics too, real quick, that I wanted to mention before we go over to the moons of Jupiter and Saturn, okay? So I didn't want to start off with the moons without saying anything about the planets themselves. Here's another little picture for you. These are Jupiter's clouds. This is Jupiter and Saturn right here. Jupiter's clouds are stretched into bands known as belts. The darker bands are called belts, and zones are the lighter bands. Also visible in this image is the large circular storm known as the Great Red Spot. So that right here is Jupiter. This is Saturn without the rings, because the rings are removed due to distraction. Saturn also has some bands, but you can see how Saturn bands are different from Jupiter bands. So that's Jupiter right there, and here is Saturn right here, okay? So the appearance of Jupiter and Saturn depends on the temperature and the resulting chemistry at the highest levels in their atmospheres. So that's what's determining what we kind of see. The rapid rotation of Jupiter and Saturn. So another feature, of course, is the rapid rotation we just mentioned. And this actually stretches the clouds into bands that run parallel to the equator. The banded structure is most clearly seen in the case of Jupiter, like here. However, Saturn shows bands parallel to its equator as well. In the case of Jupiter, the visible clouds are primarily in 3 layers that are 75 kilometers deep. The uppermost layer consists of ammonia crystals. In the middle, we have ammonia and hydrogen sulfide, and these actually form crystals of ammonium hydrogen sulfide, and in the lower layer, the clouds are made of water crystals. So there is water, but there's also other things like ammonia, hydrogen sulfide, and ammonium hydrogen hydrosulfide. So various such things are within this atmosphere. All of these substances are white in their crystallized form. So, one might think that that's just water, but actually it's all these other things as well, okay? Finally caught one live. I'm still too dumb for this side of the cat box. Aww. Hello. Hi, AB Normal. Yes, we're going live a bit earlier today. Well, a lot earlier today so that we can catch more people at various different times. Thank you so much for being here. Welcome, welcome. Yay. So that was a little bit about Jupiter. I'm skipping over some stuff because we've kind of covered it already, but those are some things about Jupiter that are interesting. Um, and I already mentioned about the zones and the belts, etc., etc. And let's read a little bit about the great red spot as well. So the upper atmosphere of Jupiter is divided into zones and belts. Hi, tricking us, making us learn, luring us in with adorable kitty cats. Absolutely. Thank you, AB Normal. Now, Seth, how are you? Hello, my friend. So, the upper atmosphere of Jupiter is divided into zones and belts. The zones are the light colored bands. So, right here, I mentioned about them. Thank you. Yes, thank you so much for liking. They are lower in temperature and higher in altitude than the belts and represent the tops of high pressure clouds that are rising upward. The belts are the darker colored bands. They represent lower pressure clouds that are sinking downward. Large cyclonic storms are sometimes seen in the atmospheres of the Jovian planets. So, gets very interesting. Baji is sleeping, yeah. The best known of these storms is the Great Red Spot on Jupiter. Right here, we don't have a color photo, but yes. The great red spot varies in size and shape, but at its maximum size, it is 40,000 kilometers across, about equal to the circumference of the Earth. Wow. So the great red spot is 40,000 kilometers across, which is about equal to the circumference of the Earth. The Great Red Spot on Jupiter is a high-pressure system in Jupiter's southern hemisphere. As air flows away from the center of the spot, it is deflected to the left by the Coriolis effect. As a result, the Great Red Spot rotates counterclockwise. So, very interesting looking thing. The Great Red Spot was first recorded by astronomers on Earth in the mid 17th century. I believe Galileo actually saw it. Maybe, unless I'm wrong. So, those are some fun facts about Jupiter and Saturn. And what we will do now is I need to make some coffee, and you can hang out with Baji, and then I'll be back, and we will be discussing the satellites of Jupiter and Saturn, or the moons of Jupiter and Saturn. I actually started this topic last night, but there was a lot of turmoil in the chat, which got me distracted. And so I thought I'll finish it up with you here today in the more afternoon timeline. What about astronomers elsewhere? Jupiter, Tamil name is Veyalan. Oh, how interesting. Thank you for sharing that. Now Sat is saying Jupiter's Tamil name is Veyalan. What about astronomers elsewhere, meaning, what is the question? Can you elaborate? And yes, please do put any messages or questions or interesting facts that you want to share in the chat. But I find it very interesting to read all your chat messages and any information you're sharing. Thank you so much in advance. Saturn, Tamil name is Shani. Yes. So I know about Shani. I think in Bengali, Jupiter is Brihaspati, unless I am wrong. Oh, you're asking about astronomers on other planets, like other places. Got it. I think in Bengali, Jupiter is Brihaspati and Saturn is Shoni, just like you're saying Shani, But I'm not sure exactly, so we should check those facts. Put any clever facts in the chat. share your language if you like, and thank you so much. Unclever is fine too, I suppose. Go for it. My specialty, Earth Tamil name is Bhumi. Oh, Bhumi as in like kind of similar to Bhumi? Bhumi? Bhumi, Fuji, Baji, Suji. Bhumi. Yay. My Tinky says hi and she wants treats. Is that your kitty cat? Yeah, Lil, one of many. Okay, sorry, I got distracted. I was typing something. Let me get up and make a coffee. Please do keep on hanging out with Baji, Fuji, and me. Oh, Baji, were you having a dreamy? Were you disturbed? Baji was disturbed. Baji was having a community dream where he dreams in the middle of everybody. And Baji was having a community dream and he got disturbed. It's okay, Baji. You go back. You go back. You go back to bed. You go back to bed. Here. Do you want a little blanket on you? Go ahead, Baji. It's okay, Baji. It's okay. It's okay. You stay. You stay here. Baji under blankie. All right, let me go make my coffee. Because I really need that. Really need that. Okay. Would you know? Do we have a Oops. Baji, you can continue to sleep, baby. Fuji's, of course, helping me. But Baji, don't worry. Hi. I'm eating too. Toasty kitty. Oh my god, this is pretty hot. Maybe I'll make noodles tonight before the gym. For now, I'll do coffee. Okay. I'm here. I am. How are you? How are you now, Seth? I'm here. Under the blanket. I am here. How are you? I am here. Okay. Igor, hello. I can see the chat messages on my Mac because I put the phone in front of Baji. Bunai is the Tamil name for cat. Aww. Igor says hi. Howdy. Okay. We will begin the moons now. Show your beautiful face. I don't feel like it today. Right now, that is. Right now, I don't know. I'm having an introverted day. I just want to do the chill live, do the kitty cats plus voiceover chat, drink my coffee, type, and cover the moons of Jupiter and Saturn, and then make some food, go to the gym, have a chill night, schedule videos, you know, that type of thing. Last night I was there showing my face. Were you here? Now, Seth? Moon Tamil name is Nilavu. Wow. Wow. Moons of Jupiter and Saturn. Moons of Jupiter and Saturn sharing the live. Okay. All right, everybody. Thank you so much for being here. Oh my gosh. Look at Baji. Look at Baji. Wait. It's the other way. Look at his pawpaw. Okay. So, thank you for being here. Thank you for joining the live. There is Fuji Baba. Here is Baji Baba. Jupiter show picture. Okay. Here is the Jupiter picture. All right, we will get started with the moons of Jupiter. Yes, Vialan. I think, is that the same as Brihashpati? Brihashpati? I think we call it Brihoshpati. Maybe I'm wrong, but we should check. But I think Jupiter in my language is Brihoshpati. Okay, so Jupiter and Saturn have many natural satellites, or many, many moons. Okay. At the time of writing of this book, the number of known moons stood at 63 satellites for Jupiter and 60 satellites for Saturn. So that is 63 and 60 for Saturn. Although the count may well be higher by the time you read this, says the authors, most of these satellites are small and irregular in shape and are on highly eccentric and highly inclined, sometimes even retrograde orbits. The small irregular satellites are probably bodies that were captured after formation of the planet. Some of the satellites, however, are large spherical bodies comparable in size to the Earth's moon that have nearly circular orbits close to the equatorial plane of their parent planet. These large satellites were probably formed at the same time as their parent planet. So our moon, as I was mentioning a bit ago, is one of the largest moons in the solar system. So we can be grateful that even though we don't have many moons, multiple moons, we do have one of the largest moons, or a giant moon. So when we talk about such a bigger moon, we think that those moons of Jupiter and Saturn were formed along with their parent planet. It is found in general that small satellites are non-spherical, so they're kind of not really very specially or very perfectly round, whereas the larger satellites are close to perfect spheres. Whether or not a satellite or any other celestial object really excuse me, is spherical depends on whether its compressional strength is great enough to resist the force of gravity. So there is this tug of war between compressional strength and the force of gravity, which kind of determines whether it's going to be spherical or some other random shape. The compressional strength of a material is the pressure required to significantly deform its shape. Engineers determine the compressional strength of different materials by putting a sample into a hydraulic press and increasing the pressure until the sample is either squashed flat or shattered, depending on how brittle the material is. For instance, iron has a compressional strength of around 4 times 10 to the 8 newtons per meter squared. So that's a lot. Typical igneous rocks have a compressional strength of around 2 times 10 to the 8 newtons per meter squared, similar to high-strength concrete, and solid ice has a compressional strength of 10 to the 7 newtons per meter squared. So, of course, ice is more brittle, if you will, but still pretty high compressional strength. For an approximately spherical body, we have found that the central pressure will be given by something like 2 pi over 3 rho squared capital G r squared, where the critical radius, our sphere, at which the pressure is just great enough to overcome the compressional strength and squeeze the object into a sphere, is determined by the relation P critical is going to be around equal to that compressional strength number, and give us some quantity for the R sphere at which this happens. So you can see how there is some specific critical radius depending on what you're mainly made of, what material you're mainly made of. Is it mainly rock, iron, ice? What is it, right? For example, for our own home planet's moon, we know that it does not have a lot of iron. We were reading about the moon the other day, and we know that we were actually looking at a few different theories of how our moon may have formed, because it actually lacks some of the diversity of material in its surface and overall what makes it up than Earth. So if it came out of the Earth, we would have expected, well, we still think that, there are a few different theories, we can talk about them, but basically the thought was that the moon seemed to be less diverse in its materials than Earth. And also it did not have the iron core or as much iron as we do on Earth and in the Earth. So there was this theory that maybe we were, something else collided with us and contributed to our, whatever collided with us, basically also had an iron core and contributed further to our existing iron core. And something else got ejected from more of the mantle of the Earth. So not the core, but closer to the surface of the Earth, some part of it got ejected, which is missing the iron richness. And that something else that got ejected is really the moon for us. So this was an explanation of why the moon, for example, does not have some of the diversity that we have here on Earth, and why the moon does not have an iron core. So exactly what some planet, moon, whatever, is made of, what materials make up mostly what it is extremely important in what shape it's going to have and things like that. The stronger of the materials of which natural satellites are made, so something like iron, rock, ice, are also more dense. So I was just now talking about our moon. In general, now we're talking about moons, right? Generally speaking, there could be stronger materials within a moon, such as iron, rock, and ice. And these are going to be more dense. So if you get a value, say, of our sphere of around 300 kilometers, though, then that doesn't depend strongly on whether the satellite is more metallic, mostly rocky, or mostly icy. Why did I say 300 kilometers? Is because we have this table of the different materials and their compressional strengths and densities, and basically at what R sphere radius will the material become more spherical, right? So if you had to bend iron into a spherical shape, what is the radius? And same thing for rock, same thing for ice. So it turns out there's a little bit of a table here. Minimum radius for spherical satellites, okay? So this is the minimum the radius has to be in order for that compression thing to happen and it becomes more of a sphere. For iron, it is 210 kilometers minimum. For rock, it is 340 kilometers minimum. And for ice, it is 300 kilometers minimum. So we're saying if your R sphere is around 300 kilometers, you might be getting something kind of mostly spherical. So of the spherical satellites in the solar system, 7 have radii of over 1,300 kilometers, which is around 0.2 times the radius of our Earth. And thus, these radii are quite big, and they're larger than any known dwarf planets. An example of a dwarf planet is, of course, many people's favorite exoplanet, Pluto. A lot of people have trouble accepting that Pluto is not a planet, but a dwarf planet. But unfortunately, we have to stick to the facts here. And as of right now, as of a long time now, Pluto has been recategorized as a dwarf planet and not a planet. Okay. So, and it turns out that a ton of the satellites, around 7 of the satellites in our solar system, actually have radius quite a bit larger than these dwarf planets such as Pluto. These 7 giant satellites we will talk about also in a bit. The giant satellites Ganymede and Titan are actually larger in radius than the planet Mercury. So not only are they bigger than Pluto, which is a dwarf planet, but guess what? There are giant satellites that are bigger than even a planet such as Mercury. Mercury, remember, the radius of Mercury was 0.38 times the radius of Earth. And so we have some moons here in the solar system that are bigger than even Mercury. The high mass density of the planet Mercury, however, means that its mass is greater than that of Ganymede and Titan combined. So Ganymede and Titan may be bigger in size than Mercury, but Mercury is actually very dense, and we talked about it a few lives ago because we covered Mercury, Venus in that live. We actually covered Mercury in more detail, I believe, a few days ago. And then we touched upon Venus, and then Venus also we covered over a couple of lives. So Mercury has this very special feature where it has a gigantic iron core. And so we think that it might have even been bigger at one point and maybe lost part of its mantle because it's extremely dense. Of course, why? Because, mass over volume. Its volume is smaller, but it has a ton of mass, and it has a ton of mass comparatively to its volume, and a lot of it is its iron core. So just because of the composition of Mercury, it has more mass, even though it is tinier in radius than something like Ganymede and Titan. So, the high mass density of the planet Mercury means that its mass is greater than that of Ganymede and Titan combined. The 4 giant satellites of Jupiter are known as the Galilean satellites. So, we also have talked about Galileo Galilei, of course, in the live in the past. He is sometimes hailed as the first modern scientist. He did observations of of the heavenly bodies, if you will, including but not limited to the moons of Jupiter that he discovered through his telescopes, and basically shed a lot of light on many things back then that were a question mark or a confusion, and all of that stuff, and further proved that we had a heliocentric solar system, things like that, and features on the moon and how the heavenly bodies are not perfect and stuff like that. And finding that another planet had moons was a big one because, remember, in the Earth-centric views, it was kind of a big deal that we have a moon. And so we thought maybe we're really special, we have a moon, but turned out that other planets also have moons, such as Jupiter. Of course, Jupiter is gigantic, so might have been easier to find Jupiter, and it's so big, and these moons are also kind of visible more easily relative to other things. And so what he found was, oh look, there is another whole planet or another whole heavenly object which has satellites of its own. So it was a very big deal. Okay, so when this was found back in the day. So, look at Baji. He's under the blanket. So the 4 giant satellites of Jupiter are known as the Galilean satellites after their discoverer, Galileo Galilei. The discovery of the Galilean satellites was an important early support for the Copernican system. So this is what I was just now mentioning. The Ptolemaic system, or the, Earth-centric system, was something that ruled for a long time. And then Copernicus was saying that Earth is not at the center, the sun is at the center. And basically, further confirmation of the Copernican system was something like this in terms of observation. In order of increasing distance from Jupiter, the Galilean satellites are Io, Europa, Ganymede, and Callisto. So we were mentioning Ganymede and Titan, moons of Jupiter and Saturn, actually, but now we're focused on the moons of Jupiter in the very first ones that were discovered. And these are, again, Io, Europa, Ganymede, and Callisto. Oh, and let me read this sort of important footnote. A few materials combine great compressive strength with relatively low density. For instance, so we were talking about the compressional strengths of different materials. So in relation to that, let me also mention this. A few materials combine great compressive strength within relatively low density. For instance, a diamond has 3,500 kilograms per meter cubed, comparable to an ordinary igneous rock, but a compressive strength of 10 to the 10 Newton per meter squared. So it has a lot of compressive strength. Thus, a diamond in the sky could be as large as 2,400 kilometers in radius before being squeezed into a spherical shape. So basically, all of this is to say, if you wanted to squeeze diamond into a spherical shape, good luck to you. Basically, it has relatively low density, but its compressional strength is extremely high. So if, say, there was a planet or a moon that was made of diamond, well, to make it spherical, it would have to be quite large. So 2,400 kilometers in radius, wow. Shine bright like a diamond. That song. In the sky. Shine bright like a diamond. Well, you can shine bright, but probably cannot become a sphere very easily. Shine bright like a diamond. Okay. So here are the giant satellites of our solar system. Are you ready? As I was saying, a lot of the moons are pretty small in the solar system. You know, like Jupiter has... Oh my God, what was that noise? There's a big noise in this... oh, I see. Next door. Okay. Sometimes there's a big noise in the neighbor and in the neighboring house, and I think it's like our house because everything is so close. So, okay. So I was mentioning that, you know, there are a lot of moons in this solar system, especially these Jovian planets like Jupiter and Saturn have a ton of moons. There are like over 60 moons of Jupiter and over 60 moons of Saturn, but many of them are pretty small and kind of like irregular, not as round and pretty like our moon, right? So our moon is special because it is one of the giant moons. So let me read to you the list of giant moons in our solar system. So for the planet Earth, we just have the one moon, of course, and its mass in terms of the Earth mass is 0.0123 times the mass of the Earth. And its radius is 0.27, the radius of the Earth. Wow. Actually, that answers my question that I was asking the other day. Give me 1 second. So, Mercury, just for reference, is 0.056 mass of Earth. Okay, so keep that in mind. Sometimes I like to compare the moon with Mercury just to see, but I think the moon is so 0.01. Oh my God, I keep losing the spot. I don't know why I didn't keep it. So Mercury is 0.056 mass of Earth. So the moon is less massive. Got it. Perfect. So the moon is 0.0123 the mass of Earth. and its radius is 0.27 the radius of Earth. So pretty big. That's pretty big for a satellite. So that is a giant moon of this solar system, our own moon. And you will see that all the other giant moons are actually slightly bigger. But we do have one of the giant moons, our moon. Jupiter's satellites, Io, has a mass of 0.0150 and a radius of 0.29 radius of Earth. So everything is in terms of Earth, the mass as well as the radius. And keep going. These moons are our moon, Io, Europa, Ganymede, Callisto, Titan, and Triton. So basically, our moon is a giant satellite. Jupiter's Io, Europa, Ganymede, and Callisto are giant satellites. Saturn's Titan is a giant satellite, and Neptune's Triton is a giant satellite. Okay? Those are the giant satellites of our solar system. 1, 2, 3, 4, 7. There are 7 giant satellites in our solar system. I call them giant moons, but I think because our moon is called the moon, we don't want to confuse people. But basically, the radii are going all the way from 0.27 our Earth to something like 0.29, 0.24, 0.41, 0.38, 0.40, 0.21. 0.41 is the radius of Ganymede, which is the one that's bigger than Mercury, because we just mentioned that a little while ago. It is bigger than Mercury, but its mass is less than Mercury's. So those are the giant moons, really quickly for you as an overview. Yeah, quite something, right? Now we will come back to the Galilean satellites. So these are, of course, the four satellites, the four biggest satellites of Jupiter, Io, Europa, Ganymede, and Callisto. But we wanted to real quick mention all the 7 biggest satellites, which I just did. So the Galilean satellites probably formed as would a miniature solar system with Jupiter at the center. So just like we all formed from the solar system, from the condensation of a gigantic gas cloud, and like the sun was made, and some of us condensated closer to the sun, like Mercury, Venus, Earth, and Mars, and some of us condensated farther away from the sun, such as Jupiter, Saturn, Uranus, and Neptune. But similar sort of sub-condensations, if you will, happened around the planets as well. Well, some of them, not all of them. In the case of Jupiter, this is very remarkable because Jupiter itself is humongous, and its moons kind of formed around it as though planets would have formed around the sun. So it's sort of a sun of its own, but it's not a sun. It's not a sun because it's a planet, because to be a sun, you would have to be kind of like a star that's doing nuclear power stuff and burning something to make some other thing and giving off heat and energy that way. So that's sort of the requirement for being a star. Our sun is turning hydrogen into helium. It does a ton of nuclear work to turn hydrogen into helium. It's burning literally for us and giving us light and heat and energy and all that. So that is the definition. Our sun is a star. But Jupiter is a planet, even though it's very big and very, very different from, say, our own planet. But that it, depending on what goes on in it, it's still considered a planet. Okay, just a very different one than ours. Nonetheless, it has a ton of moons. So the the satellites of Jupiter that we're mentioning formed as would a miniature solar system with Jupiter at the center. That is, the gas close to Jupiter was hottest, allowing condensation of only the least volatile substance, metal and rock, while the gas farther away was cooler, allowing condensation of the more volatile ices. within the Galilean satellite system, we see the familiar pattern of decreasing density with increasing distance from the parent body. So basically, the stuff that is closest, it's going to be hotter nearer to Jupiter. So the least volatile substances will be able to condensate closest to Jupiter. So metal and rock will be sort of the material that's able to condensate closest to Jupiter, while the gas farther away, where it's cooler, other more volatile substances will be able to condensate and make satellites that are made of those other more volatile ices. So it's very interesting that just by the distance from Jupiter, you can kind of tell what these materials would be, right? And we talked about Jupiter in more detail in one of our lives, where we mentioned the type of energy output that Jupiter actually puts out, and the why it does that. So Jupiter actually puts out quite a bit of energy, and it's hot close to Jupiter. Okay, so so all this must be taken into consideration when you're thinking about these satellites of Jupiter and how they might have formed and what they might be made of and things like that. So, within the Galilean satellite system, we see the familiar pattern of decreasing density with increasing distance from the parent body. So, Io has 3,600 kilograms per meter cubed is the density of Io. So, that's pretty high. Europa is going to be less, 3,000 kilograms per meter cubed. And the two outermost Galilean satellites, Ganymede and Callisto, we have around 1,900 kilograms per meter cubed. So basically, we expect Io and Europa to be maybe a little bit more dense and rocky and or metallic, we will see. And we expect Ganymede and Callisto to be maybe more icy and other types of more volatile ices. Such a low density indicates that Ganymede and Callisto cannot consist entirely of rock and metal, but must contain substantially of lower density ice. So Io, we will talk about Io now. Hi, Harper. Actually, let me take some sips of coffee. I'll let you guys chill for a bit. You can chat, put some messages in the chat if you like, put some comments in the chat. I need to take some sips of my coffee. So give me 1 second. Okay, so next we will talk about Io, which is the innermost Galilean satellite. Okay. Yay. Ooh, can we get 20 likes? Baji. Baji's thinking about getting 20 likes. Could we get that? Harper, can you like the live? Yes, I liked it. Okay, thank you so much. So give me a couple more seconds. I'm gonna catch my breath a little bit, and then we will talk about Io, and then we will talk about Europa, okay? You can watch Baji sleeping, and you can type any messages. How is everybody? I'm here. 3-hour coffee break. No. No. I'm here. Kitty, 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 kitty. Kitty cat. These are. Okay. Okay. All right. Thank you for your patience. My favorite planet is Venus or Jupiter. Aw, Venus. Yay. Apparently in astrology I'm ruled by Venus. Yay. Ooh, thank you for liking and subscribing. Thank you for liking the live and subscribing. Yay. Subatomic. Somebody left a comment. Heike left a comment. Subatomic particle is quite interesting topic. Aww. Thank you, Heike. Yay! Yay, yay, yay. Where is everyone? Is everybody just watching? That's okay. It can be a calmer live. That's all right. No worries about that. People can watch. Hi, Cade. Hello. Hi, my friend. Okay. All right, we will now cover Io. After Io, we will cover Europa as well. So it's gonna be a fun night, okay? It's gonna be a fun time. It's gonna be a fun time. My cat just farted. Good. So, Harper, this is a more studious live chat. See how everybody is behaving really well. I appreciate all the comments, but I think this is going to be a bit more calmer and more nice than the night chat. So, I am loving it, actually. Io, the innermost Galilean satellite, is the most geologically active object in the solar system. I have 2 more days until a train ride. Ooh, wow, kid. You're going on a train ride to where? Tell us. I'm so more calm. Good. And also, by the way, guys, if you're joining the live, it would be lovely if you could like the live and maybe even share it with a friend or 2 or 3 or 10 so that we can have more visibility, please. Thank you so much. I'll keep going and I'll look up and look at your comments in just a bit after I've touched upon Io. So this is the innermost Galilean satellite. It's the most geologically active object in the solar system. When Io is viewed at infrared wavelengths, the hot spots associated with active volcanoes are readily visible. The colors of Io in the visible range of the spectrum are due to the presence of sulfur and sulfur compounds. Because of Io's low surface gravity, which is only 0.18 g of the Earth, so it's like this, gravity, but much less. So 0.18 g Earth is a lot less than our own Earth's gravity. The volcanic ejecta can rise high above the surface and spread over a large area. So it's almost like it rises high, high, high above and spreads over a larger area because it's acting under a smaller gravitational acceleration. Volcanism on Io results in a layer of ejecta more than 100 meters thick being laid down every million years. Thus, any impact craters that may be created on Io are rapidly paved over by the volcanic ejecta. So it's almost like we talked a little bit about this in terms of the Earth. The Earth may also have been impacted by impact craters, but remember how we've also had volcanoes and volcanic ejecta and kind of the molten lava coming out and then cooling over time is kind of like paving the surface of the Earth. So it's almost like we had some potholes and we put on, a new layer of the road material and paved it over again to get the new shiny looking roads. So that sort of stuff, volcanism on Earth has done the same thing, and on Io too, has resulted in this layer of ejecta more than 100 meters thick that's being laid down on the surface every million years. Thus, any impact craters that may be created on Io are rapidly paved over by the volcanic ejecta. The hottest volcanoes on Io are spewing out lava that is around 2,000 Kelvin in temperature. So 2,000 kelvins in temperature. So I believe the surface of our sun is something like 5,000 kelvins. So, 2,000 kelvins is still pretty high. This is too high an internal temperature to be maintained solely by radioactive heating. I'm going to DC. Oh, nice. The crystal rainbow crystals come from volcanoes. Yes, that's very true. Um, the Earth has a lot of interesting volcanoes as well, and even our southernmost volcano, Mount Erebus, actually, even now, is actively making some of these crystals that you're mentioning. Indeed, we can get very pretty things from volcanoes sometimes. So, this 2000 Kelvin temperature that we mentioned, this is too high an internal temperature to be maintained solely by radioactive heating. Io's dominant source of heating is tidal flexing of its interior. Because Io is so close to the massive planet Jupiter, it experiences large tidal distortions. So we've talked about how these tidal forces can act on a extended body. Of course, we also talked about how we, as people, even a person would experience tidal forces, say, if you were going closer and closer to a black hole. If you were falling into a black hole, basically you would experience tidal forces. Actually, we did a calculation. We looked at a calculation some time ago, a few lives ago, where we were seeing what would be the mass of the black hole need to be if you wanted to die less horrifyingly as you're falling into the black hole, and which way should you be falling? Should you dive right in, or those types of things. So the tidal forces are very real. If you're close to a very big, massive object, such as Jupiter in this case, you will experience the tidal forces, and so does Io. And of course, we are also familiar with the tidal forces of the moon on us, right? That's what causes our tides on the planet. So that's a real effect. And just imagine Jupiter is an even bigger, more massive object, right? So anywho, so this is too high an internal temperature to be maintained solely by radioactive heating. Io's dominant source of heating is tidal flexing of its interior. So, tidal flexing, meaning that its insides are actually flexed by there's basically tides happening even to its insides, basically. And as things get flexed, there is heat being released. So, because Io is so close to the massive planet Jupiter, it experiences large tidal distortions. The orbital period of Io is 1.77 days, is equal to half the orbital period of Europa, which is around 3.55 days. The orbital resonance between Io and Europa causes the orbit of Io to change its shape continuously. Thus, the tidal bulges of Io are always changing in amplitude. So, because its orbit is changing in shape, that's another thing that happens because of the orbital resonance. The tidal bulges that are produced on it due to Jupiter are also kind of changing in amplitude. The constant flexing of Io's interior as it changes shape causes internal heating. Io has a very tenuous, so around 10 to the minus 10 atmospheres pressure of atmosphere of sulfur and sodium. So it's a very thin atmosphere of sulfur and sodium, which is continuously leaking away into the torus of charged particles around Jupiter and being replenished by fresh volcanic eruptions. So because it is so active volcanically, you would imagine maybe it would always have a thin atmosphere of sulfur and sodium, thanks to the volcanoes that are constantly erupting. But at the same time, it's so close to Jupiter, and we know that Jupiter has a very strong magnetic field causing the torus of charged particles around it, and it can easily trap things from something like Io's atmosphere. So that's what's going on, and the heating that we saw, very interesting. I kind of forgot about this actually. The fact that the fact that there is internal heating. So by the way, we actually saw that Jupiter also does some compression. There's basically been a compression of Jupiter over time, which has
and we actually looked at that calculation. The compression of Jupiter's radius doesn't even have to be that big, like the delta of its radius doesn't even have to be that big to explain some of the heat, a lot of the heat that's coming out of Jupiter. So basically, because Jupiter, again, also so extremely massive planet, when it compresses more, or something happens with its volume, basically, and it releases gravitational potential energy, that's actually a ton of energy for something like Jupiter because it's so big. And so even a little bit of overall, let's say over many, many years, it might have changed its shape down to something a little bit different. Even that small change in its radius will actually lead to quite a bit of gravitational potential energy being released, and a large energy output from Jupiter. So then imagine something like Jupiter's, closest moon, Io, or at least this is the, most remarkable closest moon. And it's a big one, and it also has important things going on in terms of it has the volcanoes and everything, and it's not a small, totally small object, but basically its insides are going through tides, like just like we see tides on our oceans. Just think about that sort of thing, but happening to your insides. In the case of Io, like its internal, even its interior experiences tides, because it is, of course, close to a much more extreme environment. It's in a much more extreme environment that is Jupiter. So there are these tidal bulges happening even of its interior, and as those flexing happens, basically changes in its shape happens, it will also release some energy, similar to kind of what we saw with Jupiter, I believe. But of course, Jupiter's is going to be more, okay? And also we are seeing that how this tidal bulging changes or happens in the case of Io is going to be kind of dependent on where it is in its orbit. These orbits, these periods are pretty fast. Its Io period is only 1.77 days. But also it has an orbital resonance with Europa, and that will make its basically experience different depending on where in the orbit it is. So this orbital resonance between Io and Europa causes the orbit of Io to change its shape continuously. Thus, the tidal bulges of Io are always changing in amplitude. So depending on what changes in its orbit is happening, also, you will see the bulges kind of change in amplitude because of that little effect as well. So very interesting. These are not your regular planet like Earth and regular moon, like our moon type of effects. These are the Earth is really a wonderful environment for us to all thrive on. For the most part, touch wood. But something like Jupiter and its moons are a much, much more extreme environment, leading to all these other more interesting features happening that we thankfully don't see with us on Earth and the moon, because as it is, the Earth too does a lot of things, right? The Earth has earthquakes, the Earth has volcanoes, so the Earth is geologically also very active. Io is the most active object in our solar system geologically. So the fact that Io has a ton of volcanoes and all of this stuff going on, it is the most active geologically. But even our Earth is pretty active. So the point is that Io, being in an extremely, probably one of the more extreme, next to the sun, it is basically in the most extreme environment possible because of its environment being Jupiter. So, consider our experience on Earth and how nice it is for the most part. And then there's Io, who is constantly having these volcanoes and constantly having tidal bulges happening that are even changing. And its orbit is super fast. And next to it is this crazy planet called Jupiter. So that's very different. So next we will talk about Europa. So that all of that was about Io, which is the first satellite closest to Jupiter. Next, we will talk about Europa. Now, I should mention that Europa is a very hot research topic. For a number of years, I'm pretty sure it's true even now, but for the last, I think, decade or so, as far as I know, it's a very hot topic and something that is actively researched in a number of research groups and labs, including but not limited to, I believe, the Jet Propulsion Lab of NASA, which is connected with, of course, Caltech. So, if you go to JPL, if you really, really want to study Europa, you should definitely look up opportunities at something like the Jet Propulsion Lab and see which groups that you could maybe work with on Europa. So we will study Europa right now, and it is one of those moons of Jupiter that have somehow stood out, and a lot of people are really interested in it. And yeah, so oh, sorry, Baji, I accidentally. I'm sorry. Sorry. I accidentally the page kind of flapped instead of turning, and it startled Baji. I am so sorry, Baji. It startled me too. Whenever somebody's startled, I'm also startled. So Europa is the next Galilean satellite, has a smooth, high albedo surface. The albedo is 0.67, so reflective. The reflection spectrum of Europa reveals that its surface is made of frozen water. So you can understand now why Europa is such a hot topic, such an active area of research. So, by the way, I actually need to charge my phone a little bit. Before launching into Europa, let's take a quick break and I will go charge my phone and I'll still hang out with everybody. And maybe I'll start to make some noodles. I don't know. But we will cover Europa here tonight on this live, maybe in like 10 minutes or so. So let's take a little breather. And we covered Io, we finished Io, we will study Europa next. It is an extremely interesting topic, so hang tight and I just don't want to be interrupted in the middle of the Europa conversation, so I want to charge my phone now. Okay? Give me 1 second. Oh. Oh, no. Here. There. And I will also put this on here so that you know we're going to talk about Europa. So Europa is next, everybody. Thank you for being in the live. Welcome to the live. Thank you for chatting. You can put any comments in the live chat, and we will be covering Europa next. Okay, here we go. Just need to charge the phone for a little while here and use the bathroom. Hi, Baji.
it's gonna snow. Looks like it's gonna snow and rain on Saturday and Sunday. Alright, I have to use the bathroom. I'll be right back. I will be right back, everybody. Thank you so much. downstairs. Baji was always here. Phone is charging. Hello, everybody. Hello. Can I stay? Yes, you can stay, Batman. Steven! Steven, Batman, how are you? Thank you for liking the live. Can you please, what am I even saying? Can you please like the live? Thank you so much. Welcome, welcome, everybody. Thank you so much for liking the live. Thank you so much for being here. Thank you, welcome. Kitty cats are here. They will want a little bit of a snack. And then we will continue. Oh, look at these two. Oh, such a cutie. You're such a cutie. Such a cutie. Oh, baby tutumi. Baby tutumi. Baby. Bijon chona. Hi, Anahi. Anahi Aguilar says hi. Hi. Spectre says okay. Okie de dokie. Hi. Hi. Okay, so the children want a bit of a snack. So I'm going to do that. I'm going to keep charging the phone and then we're going to talk about Europa, a very hot topic moon of Jupiter. And we will continue to continue. I remember you. Thank you. It is I, the voiceover lady with the kitty cats. Sometimes I'm on camera, especially for the night lives where it's a more of a lecture style. But this is more of a daytime live, during the day doing live, hanging out with the kitty cats and you, and also covering astronomy today. Yay! Yay! Hi. 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 Hello. Hello. Hello, everybody. So, Spectre, Anahi, Batman, Steven, everybody, welcome. Harper. Thank you. Thank you, Anahi. Thank you, Spectre. Thank you, Batman, Steven, Harper, everybody. Thank you so much for being here. For being here. Still charging. Okay, so hang on. Let me give them a treat too. Let me give them some snacks and I will be right with you. And hang out. We are all here. And yes, please, can you like the live? Thank you so much. Welcome. Baji. Thank you so much. Hi, Anahi. Okay, the children has gotten some snackies. Let me wash my hands. All right, we will now discuss Europa. Hello, everyone. How are you? Can you believe how much fun I'm having with this Facemoji app? Thank you, Anahi. Excited to see that you're having fun. Thank you so much. Okay, so let's see. Where should I put my phone? I might actually keep it charging and tell you about Europa and do it that way. That could be something we do. So let me do that. And the lighting is good here where I can see very nicely. Where I can see very clearly. Very clearly. Oh, let's see. I can do that. I can do that. So let me get up on the counter actually so I can sit. Baji, may I share the stool with you? So Baji likes to sit on this stool. Look at this, I'll show you. Right here. And I use it to climb on and reach higher things, and also sometimes I sit on it as well. So, hi Fuji. Fuji is now sitting on the book that we are trying to read from. I think he is saying that he will like to also teach you astronomy. It's the time for Fuji's class. Lecture by Fuji. Fuji Baba. Do you want us to study with you? Fuji Baba. Fuji Baba. Fuji. Fuji is F-U-J-I. Okay, Fuji, shall we? Actually, the granite is very cold. I think that's the reason why he's on the book. Are you cold? You can go upstairs. You can be in the bed, Fuji. Let me give him a different spot on the granite, and then he will probably go over to that spot. Shall I give you a different book, Fuji? Shall I give you a different book to sit on? Mama can certainly do that. Mama can. Ooh, Fuji, what if I made you a bed on the granite? What about this? What's this, Fuji? What's this? Oh, yes. What's this, Fuji? And what's this? What's this? What's this? This is your favorite box. What's this? And here's your mousey. Here's your mousey. Look at him. Look at what I did here. Ah. I'm going to be... Okay. So I've given him alternate things to sit on the granite, which is very cold. So I think now we're able to see the book. Okay. So, I wish I could stand the phone up like this. Like that. Okay, no. Forget it. So, Europa, the next of the Galilean satellites, has a smooth high albedo. The reflection spectrum of Europa reveals that its surface is made of frozen water. So, we have been covering Jupiter and Saturn and the moons of Jupiter and Saturn. And as part of that, we already finished the discussion on Io. And now we are on Europa. So the reflection spectrum of Europa reveals that its surface is made of frozen water. This makes it incredibly interesting as an active research area for many, many groups. And this is why, listen up about Europa. It is a very interesting topic. A high resolution image of Europa is what I have been leaving you with. This is it. See, that is a portion of Europa's surface, and it measures 34 kilometers by 42 kilometers, about half the area of Rhode Island. So we're showing you a half of Rhode Island sort of area on Europa. And basically, because we think that the surface of Europa has frozen water, it is extremely important and
interesting to think more about this and research more into it. And we have this high resolution image of Europa that you've been looking at while I was in the bathroom. So this reveals that the icy surface is fractured into numerous ice rafts and ice flows, measuring several kilometers across, similar to ice rafts seen on the Earth's Arctic Ocean. So, kind of like what the Arctic looks like is what we think that this is kind of what this looks like. And this gives us a lot of pause and lets us become very excited about Europa and its very interesting surface indeed. Because this may indicate that the outer ice layer of Europa lies atop an ocean of liquid water. So just like, the Arctic Ocean, the Southern Ocean. So by the way, the Arctic snow cap, or ice cap rather, is of course, there's the Arctic Ocean around it. And then the ocean closest to Antarctica is called the Southern Ocean. So actually, if somebody wants to name all the oceans on Earth, that could be a nice exercise. So let's see. Arctic Ocean, Indian Ocean, Pacific Ocean, Atlantic Ocean, and Southern Ocean. Are there any oceans that I missed? Somebody put that in the chat. So basically, these oceans are, of course, surrounding or underneath our own planet's ice caps. The Antarctic continent of Antarctica is basically ice all the way down to the ocean floor. And next to it is basically the Southern Ocean. So the Southern Ocean can actually, basically start to warm the ice of Antarctica right from the bottom up if it, if it wanted to, if it got warm enough and it did that. So that is actually one of the reasons why a lot of the ice melting in Antarctica too is a big concern. And if the Southern Ocean gets too warm, it could actually it's not only that the top parts would get warm and melting, but actually Antarctica could start to melt, even from the bottom. And so that's why global warming and these things are really, a hot and relevant topic. And again, I'm not an expert on global warming. And I'm not an expert on Antarctica and on ice stuff of our own planet and geology and things like that, really. But I wanted to mention that was something kind of cool that I had read at one point. So because our own planet's basically ice caps, the polar regions of our own planet are pretty interesting parts of the planet and give us a lot of... give us a very different environment to study. So it's almost like our own polar regions give us a sort of an idea for how things might be like in other environments, such as even Mars, actually, in some ways. And also something like this Europa. When we took a picture of its surface and we saw this, and it reveals this sort of icy looking surface fractured into numerous ice rafts and ice flows measuring several kilometers across, like what this is saying, similar to ice rafts seen on Earth's Arctic Ocean. This basically gave us a very sort of exciting implication, which is that maybe Europa is not too different, than something like maybe our Arctic region or something. Sort of, not really, but sort of. So I'm always gonna go to your live. Oh, thank you. Thank you so much. So anyway, this may indicate that the outer ice layer of Europa lies atop an ocean of liquid water. So if the outer ice layer is lying on top of an ocean of liquid water, then because maybe it's warm enough and cool enough for water to exist, maybe, then that would be extremely exciting, because that would indicate the presence of liquid water in another part of our solar system. So substantial evidence of a substantial amount. So we need of course the proof and evidence of it first, and this is why we probe Europa with various instruments and things like that, and we do the research on it. But basically, if we have substantial evidence of substantial liquid water at a different part of the solar system, like Europa, then that would be a very big deal indeed, okay? So this outer layer might be atop an ocean of liquid water. The extreme scarcity of impact craters on Europa would then be explained by liquid water flowing up through the cracks, then spreading out and freezing. The relatively high mean density of Europa, which is around 3,000 kilograms per meter cubed. So 3,000 kilograms per meter cubed is quite a bit. For reference, let me tell you the density of our own moon. I believe it was something like 3,600 kilograms per meter cubed. I just want to make sure real quick though. I think it was. So where was it? You know what? Forget it. I'll keep going. So basically, 3,000 kilograms per meter cubed is still pretty high. Because as we saw, in comparison, Ganymede and Callisto, which are the farther away moons of Jupiter, are only 1,900 kilograms per meter cubed. And I think our moon, I'll tell you what our Earth is. Earth's uncompressed density is something like 4,200 kilograms per meter cubed. So Earth is more dense. And Mercury is really dense. I think Mercury is like over 5,000. Actually, you know what? Let me just figure this out real quick here. It's gonna drive me nuts if I don't. Here we go. Okay, so the uncompressed densities of the terrestrial planets. Mercury is 5,400 kilograms per meter cubed. Venus is 4,200. Earth is 4,200. Mars is 3,300 kilograms per meter cubed. So these are pretty high dense, but we know that the terrestrial planets are rocky, metallic, solid, so the density is high. And something that we had mentioned earlier was also that the moon, our own moon, has a density of around 3,350. So I was close. It's still over 3,000 kilograms per meter cubed. So if something has around 3,000 kilograms per meter cubed density, you kind of now get the idea as compared to, say, Earth or our own moon, okay? Hi, Mike. Hello. Hi, Doro. Mike Hello says, "What's up from Ukraine?" Welcome to Ukraine. How are you? Thank you so much for being here from Ukraine. And Doro is saying, "At the gym, saw you were on. I see we got a troll kid in here." That's okay. It's been much more quieter and peaceful, actually, on this live. So it's all good. So basically, when I say that the density of Europa is 3,000 kilograms per meter cubed, I just wanted to give you some reference so that you're not like hanging with a number. The Earth is around 4,200 kilograms per meter cubed in density, uncompressed like, and the moon is over 3,000, but it's not as dense as the Earth, okay? So Europa, it's not as dense as the Earth, of course, but it's not that small of a density either, like Ganymede and Callisto. And also this missing impact craters. So the fact that we don't find a lot of impact craters on Europa could also be explained by liquid water flowing up through the cracks and then spreading out and freezing. So the relatively high mean density of Europa means that the icy surface and liquid ocean must be relatively thin layers atop a large central rocky core. So this is what I was also trying to kind of alluding to, which is that it's not as least density, or what's the word? It's not as small density as Ganymede and Callisto, which are farther away from Jupiter, right? So Ganymede and Callisto are farther away from Jupiter. And remember what we said about how when you are farther away from a very hot object, basically what that means is that the object is going to have things or materials that condensate at a lower temperature. So, what are those types of things? More icy types of things. So the ice can be made of not just water, but other types of ices as well, right? And so, it's not a surprise that Ganymede and Callisto, which are the moons of Jupiter farther away, have a lower density. Now, we're thinking that Europa has this icy top and liquid water underneath it, which is of course very, very exciting and a whole, thing for us to research and explore further and confirm further. But also we're saying that, well, it can't be totally just lower density kind of stuff. It has to have some sort of large central rocky core because its density is not that low. 3,000 kilograms per meter cubed is still high enough where it could have, or probably should have, a central rocky core, and atop that maybe it has this liquid water, and atop that of course maybe it has this icy surface, because this picture and the imaging on the surface of Europa reveals this sort of ice raft looking surface, which gives us a lot of excitement. So that's what's going on with Europa. It's an active research area, and there are entire research groups that only work on just Europa. So imagine the excitement of this. It's a lot, and actually, next, we will talk about Ganymede, Callisto, and wrap up the Jupiter moons, and then we will talk about Titan, which is the biggest satellite of Saturn. So, actually, what I want to do is start a new live to do that. I think I need to go start some laundry, and then I want to start a new live so that I can cover the rest of the moons and maybe even recap the moons a little bit in the new live, because I want more people to be notified of the live happening. So perhaps we could do that at the gym. The gym. Saw you were on. I see we got a troll kid in here. Good to hear. Glad it's calming down. Yeah, it hasn't been too bad today. It's been pretty doable, actually. Not too bad at all. I think I gotta cook some food, eat some food, start some laundry, and then I want to go to the gym as well. And then I think I might be able to do another live before the gym. I don't know what you guys think. Oh, hi, Niraj. Wishing you a fabulous morning. Hit the gym, get ripped. Lol, yeah, thank you. That's what I'm thinking. You know what? Let me finish up Ganymede and Callisto right now, and then I'll go do that. So Ganymede is the third Galilean satellite. I was just mentioning how it has a lower density than Europa and Io. It's at 1,900 kilograms per meter cubed. And it is the largest satellite in the solar system. So in that list of the giant moons that I talked about, Ganymede was 0.41, the radius of Earth. That is the largest radius, and also it has a mass of 0.02, the mass of Earth. So this is the largest satellite in our solar system together. Part of Ganymede's surface is dark and covered with impact craters. So impact craters is something we've been looking at a lot, and finding that a lot of the moons and even planets have them. We just saw how Europa has a scarcity of these impact craters, and that would be further sort of indication that it's got liquid water on it. But however, with Ganymede, lots of impact craters. However, part of its surface is covered with enigmatic grooved terrain. The grooves are about 10 kilometers apart and 300 meters deep. Judging from the number of impact craters lying on top of them, the grooves formed around a giga-year ago or a billion years ago. They may be stretch marks in the crust due to tectonic motions that have since ceased. So Earth actually has tectonic motions, as you know. I will show you these grooves. In fact, I will put them under the camera here soon. But basically, that's extremely interesting. The basically the grooves on wow. Ganymede's surface is dark and covered with impact craters. However, part of its surface is covered with enigmatic grooved terrain. The grooves are about 10 kilometers apart and 300 meters deep, judging from the number of impact craters lying on top of them. Wow! So because impact craters, we kind of know at which sort of era in the solar system we were impacted a lot by things that left impact craters on our surfaces of different objects in the solar system. We are thinking that these grooves formed a giga-year ago, and they may be stretch marks in the crust due to tectonic motions that have since ceased. Wow. So that's Ganymede. Then we have Callisto, the outermost Galilean satellite, has a surface that consists of dirty ice, that is frozen water with dust and hydrocarbons embedded within it, a little bit like Boston. Sometimes after it snows and then, mixes with other things, it can look a little bit like dirty snow or ice. So so Callisto, this is the fourth Galilean satellite, or the outermost Galilean satellite. Galileo, of course, discovered the first four moons of Jupiter. So the outermost Galilean satellite has a surface that consists of dirty ice that is frozen water with dust and hydrocarbons embedded within it. The surface is heavily cratered. The largest craters on Callisto have a higher albedo than the surrounding ice, since the impacting bodies that formed them broke through the superficial layer of dirty ice to reveal the pristine ice underneath. The Galilean satellites, like the terrestrial planets, show different amounts of volcanic activity. Among the terrestrial planets, the amount of internal heat, and thus the amount of volcanic activity, is determined by the size of the planet. However, among the Galilean satellites, the amount of internal heat is determined by the proximity to Jupiter. Io, the closest to Jupiter, has the most tidal heating. So I was mentioning how Jupiter is going to cause a lot of tides on Io. Literally, its insides will experience these tides. And so when you have such tidal flexing of the internal structures of Io, you will actually release heat, so tidal heating. Io is volcanically hyperactive. That's the other thing we saw, very active geologically, Io. Callisto, the farthest from Jupiter, has the least tidal heating, so because, of course, it will be least affected by Jupiter's gravitational force, because gravitation, of course, goes as r squared in the denominator. So when you're farther away, you experience less of that craziness. So Callisto is volcanically dead and is covered with impact craters. So very interesting. Callisto, farthest away from Jupiter, least tidal heating, volcanically dead, and is covered with impact craters. Because if it had a ton of volcanoes, the volcano would have paved its surface, kind of hiding the impact craters. But because it's volcanically pretty much dead, we have those impact craters and we can see them and they're there. So very, very interesting. It all kind of comes together. The very different experience on each of the moons of Jupiter, depending on where it is in the at a distance from Jupiter, Io, the closest one, Europa, the next one, Ganymede, the third one, and lastly, Callisto, the outermost one. And of course, all of these four moons, Io, Europa, Ganymede, and Callisto, are also part of the 7 giant moons of our solar system, 7 of the biggest moons in our solar system. Our own moon is also one of them. Titan is one of them, and Triton is one of them. Titan is Saturn's moon. Triton is Neptune's moon. And it's been interesting to talk about, of course, these Galilean moons of Jupiter because historically they have humongous significance in the history of science, and showing us that there are other things, other objects, which also have moons and basically satellites going around them, which took a lot of the pressure off of Earth as being such a special planet who would have a moon. And also because there are multiple moons here, each very different and each at a different distance, basically giving us four different diverse environments to look at and study if we wished. And one of them even has a huge promise of this frozen ice and liquid water underneath in the surface of it of the moon. So very, very exciting and interesting indeed that we were able to kind of see what these four moons are like. I will let you look at the pictures of Europa on the left here, Ganymede in the middle, and Callisto on the right. And each of these regions shown in the picture is around 220 kilometers by 100 kilometers, which is about the area of West Virginia. So you can look at this picture while I prep my food, actually, if you don't mind, because I want to eat and then go to the gym. So here we are. Actually, let me rotate this. So now, what you are looking at, one second. Now, what you're looking at, if you can see the letters here, A, B, and C, A is Ganymede, B is Callisto, and C, or sorry, what am I saying? A is Europa, B is Ganymede, and C is Callisto. Okay, so we've got Europa, Ganymede, and Callisto. And look at Callisto's impact craters. Isn't that so different, right? Look at these pictures. So very, very, very different indeed. Like the surface, this surface is so different than this one. And of course, these are pretty far from us. So, you know, any information that we gain at all on the moons of Jupiter is not a, you know, it's not a small feat. So I'm happy that we were able to learn about the moons of Jupiter today. We will also cover Titan soon here, but I will currently let you look at the pictures of Europa, Ganymede, and Callisto. Thank you so much for being here. Thank you indeed. Yay! There we are. Okay. Hi, Soji Mama. Hi. 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 Hi, Mama. Soji Mama is doing a little bit of what do you call? Soji Mama is doing a little bit of kneading on the blanket.
Oh, Suji, Suji, here you go. Suji Mama likes to get hugs, but then she's like, put me down, and I'm trying to put her down on something soft. Okay. Okay. Wait, what day is it today? Is it Thursday? I think it is. Hi, Sachi. Hi, everybody. If you're joining, can you please like the live? Thank you so much. Okay, Mama. Okay, I shared the live. Hi, Batman. Are you looking at Europa, Ganymede, and Callisto? Keep on doing that. And you can compare the surfaces of Europa to Ganymede to Callisto. Europa, Ganymede, Callisto. And Batman, if I go live tonight, I want you to say something relevant to planets and their moons. If not, I will be mad. So just beware. Just you beware. Now I need to start the laundry, but you guys keep on studying. Keep on studying, guys. Keep on. Keep on keeping on. Instant noodles. I think I'm gonna make noodles. Boil 2 cups of water. Break the noodles cake into 4 parts. What? Add the, yeah, cook for 3 minutes. Okay. I get it, I get it. I get it. Question is, do I have a pan? I think I have a pan in the dishwasher. Hello. 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 So once you look at this, I'm going to turn the page. There's something else I can show you. But continue to study. Continue to continue. Oh man, it smells really good. I think it's the neighbor. It's the neighbor cooking. It smells really good. Am I still live? Oh yeah. Thank you, everybody. I have to go do laundry. And then I have to eat. Appreciate everybody being here. Thank you so much. See you so very